Today's papers from Hugging Face include the following. 1. EVLM, an efficient vision language model for visual understanding, proposes a model that enhances visual understanding by efficiently combining vision and language tasks, aiming to improve accuracy and computational efficiency. 2. Internal consistency and self-feedback in large language models. surveys methods to ensure large language models maintain internal consistency and leverage self-feedback to enhance performance and reliability. 3. ChatQA bridging the gap to proprietary LLMs in long context and RAG capabilities, introduces improvements in long context understanding and retrieval augmented generation, making open models more competitive with proprietary alternatives. 4. LazyLLM dynamic token pruning for efficient long context LLM inference, discusses a technique to prune tokens dynamically, boosting efficiency during long context inferences without sacrificing accuracy. 5. The vision of autonomic computing, can LLMs make it a reality? Explores how large language models can contribute to the development of autonomic computing systems, potentially making them more autonomous and self-managing. 6. Stable Audio Open presents advancements in audio generation and processing, aiming for stability and high-quality outputs in various audio applications. 7. VisFocus prompt-guided vision encoders for OCR-Free dense document understanding proposes a new approach for dense document understanding using prompt-guided vision encoders, eliminating the need for optical character recognition OCR. 8. Visual text generation in the wild investigates methods for generating coherent and contextually relevant text from visual inputs in real-world scenarios. 9. Jumping ahead, improving reconstruction fidelity with JumpReLU sparse autoencoders, introduces JumpReLU, a technique to improve reconstruction fidelity in sparse autoencoders, enhancing their performance in data representation tasks. 10. SciCode, a research coding benchmark curated by scientists, describes a benchmark designed by scientists to evaluate and improve coding models, ensuring they meet the specific needs of scientific research. For detailed abstracts, visit Hugging Face Daily Papers. The research paper titled EVLM, an efficient vision language model for visual understanding, addresses the challenges and inefficiencies present in existing vision language models, particularly those based on architectures like Lava. The paper proposes an efficient multimodal language model designed to minimize computational costs while enhancing the model's ability to perceive visual signals comprehensively. Vision language models integrate visual and textual data to perform tasks such as image captioning, object recognition, and document analysis. Traditional methods like Lava employ a single-layer vision transformer VIT feature as a visual prompt, directly feeding it into the language model alongside textual tokens. However, this approach faces significant computational overhead, especially when dealing with long sequences of visual signals or inputs such as videos. Furthermore, the use of single-layer VIT features limits the model's ability to fully perceive visual signals. To overcome these challenges, the paper introduces 3 primary innovations employing a cross-attention mechanism similar to Flamingo for image-text interaction, utilizing hierarchical VIT features, and introducing the mixture of experts MO mechanism to enhance model effectiveness. These innovations collectively aim to balance computational efficiency with information richness, enabling the model to achieve competitive scores on public multimodal benchmarks and perform well in tasks such as image and video captioning. The proposed model architecture is based on Flamingo and primarily consists of a visual encoder, a large language model LLM, and a gated cross-attention layer. To capture more fine-grained visual signals, the model extracts hierarchical visual features from different layers of the visual encoder and increases the length of Flamingo's media tokens. The visual encoder used in the model is the EVA2 clip E+, from which hierarchical visual features are sampled uniformly from the last 40 layers of the transformer. These features are then sequentially fed into different gated cross-attention layers of Flamingo. The gated cross-attention layer enables interaction between vision and text, using learnable tokens to carry visual features, thereby ensuring efficient processing of long visual tokens without excessive computational overhead. The language model utilized is the Qwen 14 billion Chat 1.0, known for its performance in content understanding and logical reasoning. gated cross-attention layers are inserted before every transformer layer of the language model to condition it on visual inputs. The training process of the model consists of 3 stages: multimodal pre-training, multitask continual pre-training, and multimodal instruction fine-tuning. Each stage is designed to progressively enhance the model's capabilities and fine-tune its performance. During the multimodal pre-training stage, the model aims to achieve cross-modal alignment of images and text and model the intrinsic relationships within multimodal data. A large-scale dataset of image text captions and web-type multimodal data is collected and processed to ensure relevance between images and text. The dataset includes 2.5 billion image text caption data and 50 million web-type multimodal data, with a significant portion consisting of Chinese data to enhance fine-grained alignment capabilities. The training involves concatenating caption and multimodal web-type data separately to ensure each sample has up to 64 images and a sequence length of 2048. The training objective is to minimize the cross-entropy of the text tokens, and a cosine learning rate strategy is employed with a maximum learning rate of 6.4 E-4. The multitask continual pre-training stage focuses on acquiring high-level visual question answering abilities. The training data includes visual question answering VQA data, natural language processing NLP data, OCR data, detection data, and samples from the first pre-training stage to prevent catastrophic forgetting. The model's training objective remains to minimize the cross-entropy of the text tokens, and a cosine learning rate strategy is used with a maximum learning rate of 1 E-4. The model obtained at this stage is referred to as EVLM base. In the supervised fine-tuning stage, the model undergoes instruction fine-tuning to activate its instruction following abilities. This stage involves using high-quality instruction tuning data, including user instruct data, multimodal document chart data, and math problems. The LLM is frozen, and only the cross-attention layers and the last quarter of the VIT layers are tuned, resulting in a model called EVLM chat. To achieve better performance, the model employs a mixture of experts MO architecture during fine-tuning. The MO architecture scales the gated cross-attention layer, resulting in multiple fine-grained experts that improve the model's performance by specializing in different aspects of the input data. The same training data and configuration of the dense baseline model are used with the LLM frozen and only the cross-attention layers in the last quarter of the VIT layers tuned. The model obtained at this stage is referred to as EVLM-MO. The evaluation of the model involves various multimodal tasks to assess its visual understanding and reasoning capabilities. The model's performance is tested on benchmarks such as VQO2, GQA, ScienceCode set, VisWiz, TextDQO, DAFDQO, ChartQA, A2 diagram, MME, MBCN, and POPIC. The results show that EVLM chat and EVLM mode demonstrate superior performance compared to other models across these benchmarks. For instance, in the ScienceCode, EVLM chat and EVLM mode achieved 86.4% and 86.8% accuracy, respectively, outperforming previous models with higher resolution. In addition to general VQA benchmarks, the model's performance is evaluated on text-oriented VQA benchmarks, which require detailed visual perception for tasks like diagram understanding and associated question answering. The results show that EVLM-MO and EVLM chat achieve high accuracy on datasets such as AI2 diagram, demonstrating the model's ability to comprehend complex text details within images. The model's visual understanding and reasoning abilities are further evaluated on general multimodal benchmarks, encompassing a broader range of evaluation aspects and requiring more complex reasoning capabilities. The model demonstrates commendable performance, highlighting its adaptability and capability across various disciplines. One of the key capabilities of the model is dense caption, which involves generating detailed, accurate, and illusion-free image descriptions. The process for generating high-quality dense descriptions includes multiple steps: generating multiple descriptions, authenticity verification, recombination of verified sentence into coherent descriptions, and stylization using GPT-4. This approach ensures that the model produces fluent, detailed, and accurate image descriptions, enhancing its performance in practical applications. The model also excels in video captioning, understanding video sequences, and generating detailed descriptions of actions, environments, and objects. The attention mask is designed to enable the model to acquire all visual information about the video, ensuring each textual token accesses all related visual features. The model's performance in video-dense captioning is verified using publicly available data sources, achieving high scores and demonstrating its ability to depict detailed video content accurately. In conclusion, the EVLM model presents an efficient approach to handling large-scale image text, pre-training, and demonstrates competitive results on public benchmarks, particularly in image and video-dense captioning. Future work includes employing more powerful, larger-scale language models and exploring the capability of video understanding under extremely long sequences using cross-attention mechanisms. The detailed methodologies and comprehensive evaluation of the model highlight its effectiveness and potential for further advancements in vision language understanding. The paper, titled Internal Consistency and Self-Feedback in Large Language Models, a survey delves into the intricacies of how large language models LLMs like ChatGPT perform and where they falter, particularly focusing on issues of internal consistency and the generation of hallucinations. These models have shown significant advancements in natural language processing, demonstrating capabilities akin to basic human intelligence, such as reasoning and learning from examples. However, they often produce inconsistent responses, exhibit illogical reasoning, and generate content that may not be factually accurate. To address these shortcomings, various self-strategies, such as self-consistency, self-improve, and self-refine, have been developed. These strategies involve LLMs evaluating and updating their own outputs to improve performance. The paper introduces a unified theoretical framework termed internal consistency, which aims to provide coherent explanations for the lack of reasoning in the presence of hallucinations in LLMs. Internal consistency is assessed by examining the coherence among the model's latent layer, decoding layer, and response layer based on sampling methodologies. The paper further expands upon the internal consistency framework by introducing a streamlined yet effective theoretical framework called self-feedback. This framework consists of two main modules: self-evaluation and self-update. Self-evaluation captures signals related to internal consistency, while self-update leverages these signals to enhance either the model's response or the model itself. The self-feedback framework has been employed in numerous studies and is systematically classified by tasks and lines of work in the paper. The authors also summarize relevant evaluation methods and benchmarks and delve into the question of whether self-feedback truly works. They propose several critical viewpoints, including the hourglass evolution of internal consistency, the hypothesis that consistency is almost correctness, and the paradox of latent and explicit reasoning. The paper concludes by outlining promising directions for future research and open sourcing the experimental code, reference list, and statistical data. Large language models are expected to respond accurately, but often they exhibit deficient reasoning or generate hallucinations. To mitigate these issues, various strategies involving the model evaluating and updating itself have been initiated. However, there has been a lack of a unified perspective on summarization, as existing surveys predominantly focus on categorization without examining the motivations behind these works. The paper aims to fill this gap by summarizing a theoretical framework called internal consistency, which offers unified explanations for phenomena such as the lack of reasoning and the presence of hallucinations. Internal consistency assesses the coherence among LLM's latent layer, decoding layer, and response layer based on sampling methodologies. Expanding upon this framework, the paper introduces self-feedback, which consists of self-evaluation and self-update modules. Self-evaluation captures internal consistency signals, while self-update uses these signals to enhance the model's response or the model itself. This framework has been employed in numerous studies, and the paper systematically classifies these studies by tasks and lines of work. It also summarizes relevant evaluation methods and benchmarks and explores whether self-feedback truly works. Several critical viewpoints are proposed, including the hourglass evolution of internal consistency, the consistency is almost correctness hypothesis, and the paradox of latent and explicit reasoning. The paper outlines promising directions for future research and has open-sourced the experimental code, reference list, and statistical data. The paper identifies a fundamental category called internal consistency as central to the core challenges faced by LLMs. At the surface level, even robust language models like GPT-4 can generate inconsistent responses to identical queries. This inconsistency is caused by using trivial stochastic sampling methods during decoding. At the deepest layer, specific attention heads and latent states are related to the faithfulness of the responses, and increasing their weights can consistently enhance the faithfulness of the answers. The paper illustrates this phenomenon using GPT-4 as an example. The authors believe that internal consistency is a more profound topic underlying issues of reasoning and hallucinations. They argue that only when the model exhibits internal inconsistency can strategies like self-consistency, self-refine, and self-correct be employed to elevate LMS reasoning abilities and alleviate hallucinations. These strategies are referred to as internal consistency mining, which involves developing methods to ensure LMs consistently express their understanding learned from the corpus. The issues of lack reasoning and exhibit hallucinations in models represent persistent concerns, with their prominence in the academic community increasing. The paper compares these two pivotal issues to demonstrate the necessity of examining them from the perspective of internal consistency. Definitions of these issues, real-world examples, and benchmark examples are provided to illustrate their overlap. The authors argue that lack reasoning and exhibit hallucinations share the same essence and require a unified perspective for analysis. They adopt the term internal consistency mining to encompass methods aimed at reasoning elevation and hallucination alleviation. To enhance the model's internal consistency, scaling the model's parameters is the most direct approach. However, this does not address the fundamental problem of weak consistency. The authors propose the self-feedback theoretical framework, which includes self-evaluation and self-update. This framework enables models to self-evaluate their outputs and self-update their structure or responses. Notable examples include self-consistency, which prompts the model to generate multiple answers and select the final answer through a majority voting strategy, thereby enhancing reasoning capabilities. Another example is self-contradict, which induces models to generate diverse content and check for contradictions, allowing the model to resolve contradictions autonomously to reduce hallucinations. The paper highlights that during self-evaluation, it is possible to inspect not only the model's responses but also its logits and latent states. Various updating methods include adding, deleting, merging, and looping responses, establishing decoding strategies aimed at consistency, and activating authenticity in latent states. The combination of self-evaluation and self-update constitutes the self-feedback framework. The authors also discuss several related surveys that focus on self-prefix strategies. They compare these surveys with their work, highlighting the advantages of their proposed frameworks, such as the internal consistency theoretical framework and the self-feedback theoretical framework. The author's framework includes self-evaluation, consistency signal acquisition, and self-update, which are characterized by simplicity and comprehensiveness, poised to inspire further research. They summarize a broad array of self-evaluation strategies that extend from model responses to latent space exploration, allowing the capture of diverse feedback signals. The paper is structured logically to provide a comprehensive understanding of LLM's internal consistency and self-feedback frameworks. The research begins with the problem of low internal consistency in LMS, discussing its manifestations, underlying causes, and potential solutions. And the authors formalize internal consistency as the sampling-based consistency of model expressions across different layers, enhancing response, decoding, and latent consistency. To improve internal consistency, the authors propose internal consistency mining across different layers. While scaling up the model is an intuitive solution, it comes with various cost-related challenges. The focus is on the self-feedback theoretical framework, which includes self-evaluation, consistency signal acquisition, and self-update. Models obtain different forms of internal consistency signals through self-evaluation and use these signals to self-update either responses or the model itself. The authors explore 6 lines of work in consistency signal acquisition and 7 lines of work utilizing the self-feedback framework. The lines of work for reasoning elevation include reasoning topologically, refining with responses, and multi-agent collaboration. The lines of work for hallucination alleviation include refining the response iteratively, mitigating hallucinations during generation, decoding truthfully, and activating truthfulness. In addition to the central topics, the authors discuss other tasks that utilize the self-feedback framework but do not aim to address low internal consistency. The paper also summarizes relevant evaluation benchmarks and methods and delves into the question of whether self-feedback really works. It provides a more insightful analysis based on the proposed perspective on internal consistency. The authors conclude by outlining challenging research directions for the future. They clarify the discussion boundaries to ensure logical coherence and readability, focusing on reasoning elevation and hallucination alleviation without systematically reviewing these aspects. The methods discussed aim to enhance internal consistency, but if their primary goal is not to improve internal consistency, they remain outside the scope of this survey. The survey exclusively explores internal consistency and does not examine the interplay between internal and external consistencies. The focus is on the model's self-awareness, self-assessment, self-correction, and minimal human intervention during self-evaluation and self-update. In summary, the paper presents a comprehensive survey of internal consistency and self-feedback mechanisms in large language models. It introduces theoretical frameworks and strategies to enhance reasoning capabilities and reduce hallucinations, providing a unified perspective for addressing these challenges. The proposed frameworks and methods offer a robust foundation for future research and development in improving the performance and reliability of LLMs. The research paper titled ChatQA 2 Bridging the Gap to Proprietary LLMs in Long Context and RAG Capabilities presents the development and evaluation of ChatQA 2, a Llama 3-based model designed to close the performance gap between open-access large language models LLMs and proprietary models such as GPT-4 Turbo. The paper focuses on enhancing the capabilities of LLMs in long context understanding and retrieval augmented generation RAG, which are crucial for processing large volumes of information that exceed the limits of a single prompt. These capabilities are complementary depending on the specific tasks and computational budgets. In recent years, the Open LLM community has made significant strides in advancing open access models, including notable developments such as Llama 370 billion Instruct by Meta AI, Qwen 272 billion Instruct by Alibaba Qwen, Nemotron 4 340 billion Instruct by NVIDIA, and Mixtral-8x22 billion-8x22 billion-Instruct-V0. Despite these advancements, there remain performance disparities when compared to proprietary models in several domains. Additionally, specialized open access models have been developed for key domains, such as DeepSeek Coder v2 for coding and math, ChatQA 1.5 for conversational QA and RAG, and Internval 1.5 for vision language tasks, which can rival GPT-4 Turbo in certain areas. The trend of extending the context window length in LLMs has gained traction in both the industrial and research communities. Leading proprietary LLMs support very large context windows, enabling them to accommodate several hundred pages of text in a single prompt. For instance, GPT-4 Turbo supports a 128K context window, while Claude 3.5 Sonnet offers up to 200K tokens. Gemini 1.5 Pro impressively supports up to a 10M context window. In response, open access LLMs have also made significant progress, with models like Qwen 272 billion Instruct and Yi 34 billion supporting 128K and 200K context windows, respectively. However, reproducing these models is challenging due to missing training data and technical details, and their evaluations are often based on synthetic tasks that do not accurately represent real performance. Long context capability and RAG are sometimes viewed as rival techniques, but they are, in fact, complementary. An LLM with a long context window can process large volumes of text as a prompt or use retrieval methods to efficiently extract relevant information from extensive text, depending on the task and trade-offs between accuracy and efficiency. RAG has efficiency advantages and can easily retrieve relevant context for query-based tasks from billions of tokens, a feat long context models cannot achieve. Conversely, long context models excel at tasks such as summarizing entire documents, where RAG may fall short. Therefore, a state-of-the-art LLM needs to excel at both capabilities, providing options for different tasks based on accuracy and efficiency requirements. The key contributions of this paper include the following. First, the context window of Llama 370 billion was extended from 8K to 128K tokens through continuous pre-training on a mix of datasets, including Slim Pajama with upsampled long sequences. A three-stage instruction tuning process was then applied to enhance the model's instruction following, RAG performance, and long context understanding capabilities. Second, the resulting Llama 3 ChatQA 270 billion 128K model achieves performance comparable to GPT-4 Turbo on many real-world long context tasks and surpasses it on RAG benchmarks. The study also found that a state-of-the-art long context retriever can alleviate the context fragmentation issue in RAG, further improving results. Finally, the paper provides extensive comparisons between RAG and long context solutions using state-of-the-art long context LLMs. The methodology involved two main steps. First, the context window of Llama 370 billion base was extended from 8K to 128K tokens through continued pre-training on a mix of datasets with long sequences. The rope base frequency was increased from 500,000 to 150M, and the model was trained with a batch size of 32 to fit 4 million tokens in a batch over 2,000 steps, covering 8 billion tokens in total. Special characters were used to separate different documents, as using reserved tokens like BIOS and EOS signaled the model to ignore previous chunks of text after pre-training, which was not helpful for adapting to longer contexts. Second, a three-stage instruction tuning process was implemented to enhance both long context understanding and RAG performance. Initially, the model was trained on high-quality instruction following datasets, followed by a blend of conversational QA data with provided context. These two stages involved relatively short contexts, with a maximum sequence length of 4K tokens. To handle very long context sequences up to 128K tokens, a long SFT dataset was collected. This dataset included existing long context datasets for sequences less than 32K and synthetic datasets for sequences between 32K and 128K. The final blended dataset was used for training with a learning rate of 3E-5 and a batch size of 32. To address the issues in the current RAG pipelines, such as context fragmentation and low recall with small top k, the study proposed using the latest long context retriever, the E5 Mistral embedding model, which supports thousands of tokens. The evaluation benchmarks included three categories: long context benchmarks beyond 100K tokens, medium long context benchmarks within 32K tokens, and short context benchmarks within 4K tokens. The model was evaluated on various real-world tasks from Infinite Bench, Scrolls, Long Bench, and ChatRAG Bench. The results demonstrated that the Llama 3 ChatQA 270 billion model performs competitively on tasks requiring long context beyond 100K tokens and achieves high accuracy on medium-long context benchmarks within 32K tokens. On short context tasks within 4K tokens, the model also achieved high accuracy, confirming its versatility. Additionally, the study found that for tasks within 32K tokens, long context solutions slightly outperform RAG, while for tasks beyond 100K tokens, RAG methods outperform long context solutions. In conclusion, ChatQA 2 successfully bridges the gap between open access LLMs and proprietary models, offering flexible solutions for different tasks with specific accuracy and efficiency requirements. The detailed technical recipe and comprehensive evaluation benchmarks provide a robust framework for further development and comparison. The study emphasizes the complementary nature of long context capability in RAG, highlighting the importance of excelling in both areas to meet the diverse needs of downstream tasks. The academic research paper titled LazyLLM Dynamic Token Pruning for Efficient Long Context LLM Inference introduces a novel method aimed at enhancing the efficiency of large language models LLMs when handling long prompts. The paper addresses the bottleneck encountered in the inference process of transformer-based LLMs, specifically focusing on the pre-filling stage where the key value KV cache for the entire prompt is computed to generate the first token. This process, known as the time to first token TTFT, can be significantly slow for long prompts, thereby impacting the overall efficiency of the model. The inference process of LMS is divided into two sequential stages: the pre-filling stage and the decoding stage. During the pre-filling stage, the model computes the KV cache for each token in the prompt, which is used to generate the first token. This stage is crucial as it sets up the necessary data for the decoding stage, where subsequent tokens are generated iteratively using the cached KV. However, for long prompts, the pre-filling stage can become a substantial bottleneck due to the quadratic increase in computational costs associated with computing attention scores for all tokens. This results in a prolonged TTFT, which is detrimental to the efficiency of LLM inference. To address this challenge, the paper introduces LazyLLM, a dynamic token pruning technique that selectively computes the KV for tokens deemed important for the next token prediction. Unlike static pruning approaches that prune the entire prompt at once, LazyLLM dynamically selects different subsets of tokens at each generation step. This dynamic selection process allows the model to adaptively prune and revive tokens as needed throughout the inference process, ensuring that only the most relevant tokens are processed at each step. The motivation behind LazyLLM is grounded in the observation that many tokens in a long prompt may be redundant for generating the first token. Profiling results on the long-bench benchmark reveal that the attention scores of input tokens with respect to the first generated token are often sparse. This indicates that numerous tokens do not significantly contribute to the next token prediction and can be pruned without affecting the output quality. LazyLLM implements a layer-wise token pruning strategy. In each generation step, the importance of tokens is measured using the attention scores from the previous transformer layer. Tokens with lower importance scores are progressively pruned as the input sequence passes through the transformer layers. To manage the dynamic nature of token importance, LazyLLM employs a top K percentile selection strategy to determine the threshold for pruning tokens at each layer. A key challenge addressed by LazyLLM is the need to handle tokens that are pruned at one step but may become relevant in later steps. To avoid recomputing the KV cache for these tokens, LazyLLM introduces an auxiliary cache key, aux cache. The aux cache stores the hidden states of pruned tokens, allowing them to be efficiently retrieved and recomputed when they become relevant in subsequent steps. This caching mechanism ensures that each token is computed at most once, maintaining computational efficiency. The paper evaluates LazyLLM on two large language models, Llama 2 7 billion and XGen 7 billion, using the long-bench benchmark. Long-bench includes multiple datasets covering various tasks such as single-document QA, multi-document UA, summarization, few-shot learning, synthetic tasks, and code completion. The evaluation compares LazyLLM with baseline methods, including standard LLM inference, random token drop, static token pruning, and prompt compression. Results demonstrate that LazyLLM consistently achieves significant TTFT speedup with negligible accuracy loss across different tasks. For instance, in the multi-document QA task, LazyLLM accelerates the pre-filling stage of the Llama 2 7 billion model by 2.34 times while maintaining accuracy. Additionally, LazyLLM shows better performance retention compared to other pruning methods, particularly in scenarios requiring dynamic adaptation of token importance. The technical implementation of LazyLLM involves several key components. First, the attention map of each transformer layer is used to measure the importance of input tokens. Tokens are pruned based on their attention scores, with those falling below the top K percentile threshold being removed from subsequent computations. This progressive pruning approach ensures that tokens are pruned in a manner that optimizes computational efficiency while retaining performance. Moreover, the aux cache plays a crucial role in LazyLLM's dynamic pruning mechanism. During the pre-filling stage, pruned tokens' hidden states are stored in the aux cache, allowing for efficient retrieval and recomputation in later steps. This mechanism ensures that the model can dynamically adapt to changing token importance without incurring excessive computational overhead. The paper also provides a detailed analysis of the impact of LazyLLM on overall generation speed and prompt token computation. It is observed that LazyLLM reduces the total number of tokens computed during inference, leading to additional speedup in the overall generation process. This reduction in computation is particularly beneficial for tasks with long prompts, where the efficiency gains are more pronounced. In conclusion, LazyLLM offers a practical and effective solution for improving LLM inference efficiency under long context scenarios. By dynamically pruning tokens and leveraging the aux cache for efficient recomputation, LazyLLM reduces TTFT and overall computational load while maintaining high accuracy. The method's seamless integration with existing transformer-based LMS, coupled with its training-free nature, makes it a valuable contribution to the field of efficient LLM inference. The extensive experimental results validate the efficacy of LazyLLM across various tasks, highlighting its potential to enhance the performance of large language models in real-world applications. The academic paper titled "The Vision of Autonomic Computing: Can LLMs Make It a Reality?" explores the potential of large language models LLMs to realize the vision of autonomic computing ACV. This vision, proposed over 2 decades ago, aims for computing systems that self-manage akin to biological organisms, adapting seamlessly to changing environments. Despite significant research efforts, achieving ACV has been challenging due to the dynamic and complex nature of modern computing systems. The authors propose that recent advancements in LLMs, with their extensive knowledge, language understanding, and task automation capabilities, offer promising solutions to these challenges. The introduction emphasizes the increasing complexity of computing infrastructure and the necessity for self-managing systems. Traditional approaches to autonomic systems, often reliant on rule-based mechanisms and predefined policies, have struggled to adapt to modern dynamic environments. Significant progress has been made towards ACV through the development of self-adaptive and self-managing systems, but the realization of ACV remains elusive due to numerous grand challenges, many hinging on breakthroughs in AI. LLMs, with their capabilities in anomaly detection and incident mitigation, present a significant leap forward in creating truly autonomic systems. To systematically assess the feasibility of achieving ACV using LMS, the paper proposes studying this within the context of microservice self-management, a popular architecture for managing cloud services. Specifically, an LLM-based multi-agent self-management framework for microservices introduced, and its performance is assessed using a live online evaluation benchmark built on the SockShop microservice demo project. The background and related work section delves into the principles of autonomic computing, which aims to develop self-managing systems to reduce its management complexity and costs, while increasing system reliability and performance. This concept is inspired by the biological autonomic nervous system, which autonomously regulates functions such as heart rate and body temperature. The ACV paper identified 4 key objectives of self-management: self-configuration, self-optimization, self-healing, and self-protection. The MAPE-K loop monitor, analyze, plan, execute, and knowledge provides a structured approach for implementing self-managing capabilities, forming the foundation of self-adaptive and self-management systems. The paper reviews various aspects of autonomic systems, highlighting advancements in self-adaptive systems to handle uncertainties and runtime variabilities, as well as self-protecting capabilities in terms of security risks. These principles have been applied beyond software systems to areas such as robotics, autonomous driving systems, and digital twins. Traditional autonomic systems often relied on rule-based approaches and predefined policies, which, while effective in certain contexts, were limited in handling complex, dynamic scenarios. Recent advancements in AI and ML have introduced new possibilities, enhancing self-managing capabilities through deeper insights and automation. In the context of cloud-native applications, cloud computing offers scalable resources, cost efficiency, and flexibility through on-demand access to computing power, storage, and applications. However, managing these applications poses significant challenges, including ensuring security, navigating complex microservices architectures, maintaining observability, managing resource allocation, and ensuring reliable performance and scalability. Tools like Kubernetes and Prometheus aid in managing these applications, but lack comprehensive high-level management features aligned closely with user intent. The paper then discusses the integration of LLMs into Kubernetes management as a promising approach to overcoming the limitations of traditional methods. Examples include GenKubisec, which applies LLM-based methods to detect and remediate Kubernetes configuration file misconfigurations, and K8sGPT, which provides natural language-based diagnostics and issue triaging for Kubernetes clusters. These advancements highlight the potential of LMS in enhancing AIOps tasks within cloud service management, such as data collection, root cause analysis, and incident mitigation. The authors propose a hierarchical two-level autonomic management architecture, where high-level group managers handle complex tasks and low-level autonomic agents focus on specific service components. This architecture simplifies the traditional MAPE-K design by integrating planner and executor modules in LLMs. Low-level autonomic agents manage specific service components, executing tasks and monitoring their health through a plan-execute feedback loop. High-level group managers coordinate complex tasks across multiple services, breaking down tasks into subtasks for low-level agents, ensuring optimal performance and reducing the need for human intervention. To evaluate the performance of the proposed system, a 5-level taxonomy of autonomous service maintenance is introduced, inspired by the 6 levels of autonomous driving. The levels range from simple step following L1 to full self-maintenance L5. Tasks are categorized into imperative L1, L2, and declarative L3, L4, L5. The SockShop microservice demo is used as an online live evaluation benchmark, introducing faults and performance issues to test the system's self-management capabilities. Tasks include pod failure, CPU stress, and rising traffic. The experiment setup involves deploying the SockShop on a Minikube cluster and implementing the agent-based management system using Autogen RabbitTMQ and GPT-4 Turbo. The evaluation focuses on the efficiency and quality of task completion, with metrics such as the number of steps taken, communication rounds, and task fulfillment rates. Results for L1 and L2 tasks applied to low-level autonomic agents showed high completion rates, with L1 tasks achieving 100% and L2 tasks 87%. The completion rates for L3, L4, and L5 tasks were lower, reflecting the increased complexity of higher-level self-management tasks. However, the low-level autonomic agent demonstrated significant potential, achieving Level 3 autonomy in self-optimization and self-healing. For tasks applied to the high-level group manager, the number of steps and communication rounds were higher due to the added complexity of coordination. The task completion rate for L3, L4, and L5 tasks was higher than for corresponding low-level tasks, suggesting that a hierarchical management structure can improve overall task completion rates. The paper concludes by discussing potential improvements and future research directions. These include exploring alternative LLM-based management systems with additional modules for incorporating domain knowledge and improving reasoning capabilities. Expanding the evaluation benchmark to include tasks beyond microservice management and covering more diverse failure scenarios would provide a more comprehensive assessment of the system's capabilities. The authors suggest that the proposed agent-based management system could be generalized for existing Kubernetes management frameworks, enhancing their capabilities in autonomic service management. In summary, this study presents a novel approach to advancing the vision of autonomic computing by leveraging large language models within a hierarchical multi-agent framework for microservice management. The findings demonstrate significant progress towards achieving ACV, particularly in Level 3 autonomy, and set the stage for future research to address remaining challenges and push the boundaries of self-managing computing systems further. The research paper Stable Audio Open by Stability AI explores the development and performance of an open-weight, text-to-audio generative model trained using Creative Commons CC license data. This paper emphasizes the importance of accessible generative models, highlighting that most existing models are private and not available for artists or researchers. The authors aim to present an alternative that is not only open but also competitive with state-of-the-art models. To provide context, the paper begins with an introduction to the landscape of text-conditioned generative audio models. Despite significant research efforts in this domain, many models remain inaccessible due to their private nature or restrictive licenses. The training datasets for these models often lack clear documentation regarding their licensing, posing challenges for their use in public or academic projects. In contrast, Musigan is an open model with well-documented training data, but it is trained exclusively on copyrighted material. The authors of this paper set out to create a model that adheres to transparent data practices and provides publicly available weights and code, facilitating open research and artistic creation. The core of the Stable Audio Open model is its architecture, which is divided into 3 main components: an autoencoder, a text embedding mechanism, and a diffusion transformer DIT. The autoencoder, with 156 million parameters, compresses raw waveforms into a latent space representation, making the data more manageable for subsequent processing. It consists of an encoder that uses convolutional blocks to downsample and expand the channel dimensions of the waveforms, and a decoder that reconstructs the waveforms using a mirrored structure of the encoder. The autoencoder employs variational techniques with a latent size of 64, balancing compression efficiency with reconstruction quality. The text embedding mechanism leverages a T5-based model with 109 million parameters for text conditioning. This replaces the previously used clap-based text conditioning in Stable Audio 2.0, providing more effective integration of textual information into the audio generation process. The diffusion transformer, with 1,057 million parameters, operates within the latent space created by the autoencoder. It uses a standard transformer architecture with stacked blocks of attention layers and multi-layer perceptrons (MLPs), enhanced with rotary positional embeddings for improved attention mechanisms. The DIT is conditioned using text, timing, and time-step signals, enabling variable-length audio generation up to 47 seconds. This flexibility allows the model to generate audio segments of various lengths by filling the remaining time with silence, which can be trimmed during post-processing. Training data for the model is sourced from Freesound and the Free Music Archive FMA, both of which provide CC license recordings. To ensure no copyrighted content is included, the authors employed automated and manual review processes. For Freesound, they used the PANS tagger to identify music-related tags and flagged potential copyrighted material for removal. For FMA, they conducted a metadata search against a large database of copyrighted music, followed by human review to eliminate any flagged content. This rigorous filtering resulted in a dataset comprising 486,492 recordings, totaling approximately 7,300 hours of audio, all verified to be CC licensed. The training process involved multiple stages. The autoencoder was trained first, using a combination of reconstruction loss based on perceptually weighted multi-resolution STFT, adversarial loss with convolutional discriminators, and KL divergence loss. Training was performed on NVIDIA IAIA 100 GPUs, with the encoder trained for 183 hours and the decoder for an additional 273 hours. The DIT was trained using a noise prediction approach following the V-objective method, with inference steps executed using the DPM solver for 100 steps and classifier-free guidance for quality control. This training took 338 hours on 64 100 GPUs. Evaluation of the model was conducted using established metrics such as Felpinal-3, KOPAST, and CLAP score. These metrics assess the realism, semantic correspondence, and adherence to text prompts of the generated audio. The model was tested on the AudioCaps dataset for sound generation and the Song Describer dataset for music generation. Results showed that Stable Audio Open outperformed comparable baselines, particularly in sound and field recording synthesis. However, it was less competitive in music generation due to the limited quality of training data for music. The paper also addressed concerns about memorization, where generative models might reproduce training data exactly. Using the LazyLLM audio encoder, the authors identified repeated recordings within their training set and examined the model's outputs for potential memorization. No instances of exact memorization were found, indicating the model's ability to generate novel content rather than replicating the training data. Inference speed is a critical aspect for practical applications, and the model demonstrated efficient performance on consumer-grade GPUs. It achieved 8 inference steps per second on an RTX 3090, 11 steps per second on an RTX A6000, and 20 steps per second on an H100 GPU, making it accessible for broader use in academic and artistic projects. The paper concludes by highlighting the significance of releasing Stable Audio Open with a focus on evaluation, data transparency, and accessibility. The authors acknowledge some limitations, such as challenges in generating audio for prompts with connectors or intelligible speech. They also note that the model was primarily trained with English text, which may affect performance with other languages. Despite these limitations, Stable Audio Open represents a significant step towards accessible and high-quality generative audio models, with potential applications in various fields requiring sound synthesis. Overall, Stable Audio Open provides a comprehensive overview of the development, training, and evaluation of an open-weight text-to-audio model. It emphasizes the importance of transparent data practices and accessible model weights, setting a precedent for future research and applications in generative audio. The research paper titled VisFocus Prompt Guided Vision Encoders for OCR-Free Dense Document Understanding presents significant advancements in the domain of visual document understanding (VDU). The main objective of VDU is to extract meaningful information from digitized documents, such as PDFs or images, extending beyond the scope of traditional optical character recognition (OCR). This field encompasses various tasks, including ChatQA, ChatQA, key value identification in forms, entity extraction, and document classification. Traditional VDU approaches have primarily relied on OCR to extract textual information from documents. These methods involve using vision language models where the text component is explicitly extracted using external OCR models. The extracted text, along with spatial features and visual tokens, is then used to generate predictions. However, the OCR-based approach has several drawbacks. It adds additional latency and computational costs due to the pre-processing step, and errors originating in the OCR step can propagate to the vision language model, deteriorating its performance. In response to these limitations, OCR-free approaches have emerged. In these methods, the document image is directly fed into the vision language model, bypassing the need for explicit OCR text extraction. The architecture typically consists of a visual encoder followed by a language model which receives the visual representation in the input query. This model is expected to internally learn to read and perform the downstream task without relying on OCR input. Extensive pre-training is required to endow the vision model with reading capabilities. The VisFocus method introduces a novel approach to OCR-free VDU by directly coupling the vision encoder with the language prompt. The key innovation in VisFocus is the replacement of downsampling layers with vision language merging attention VLM layers that receive the input prompt and allow the model to highlight relevant parts of the document while disregarding others. Additionally, a novel pre-training task, Localized Mask Prompt Modeling (LMPM), is proposed. This task uses language masking on a snippet of the document text fed to the visual encoder in place of the prompt, empowering the model with focusing capabilities. Consequently, VisFocus learns to allocate its attention to text patches pertinent to the provided prompt. The architecture enhancements in VisFocus are designed to better exploit the vision encoder's capacity by coupling it directly with the language prompt. Traditional approaches typically input queries exclusively to the language component, necessitating the visual features to encompass the entire document. In contrast, VisFocus inputs the prompt to both the language model and the vision encoder. This coupling enables the model to focus on specific text patches instead of processing the entire text. The result is a significant improvement in performance, achieving state-of-the-art results on various benchmarks. The VisFocus architecture consists of a visual encoder based on the SWIN transformer, chosen for its hierarchical design that captures both local and global information effectively. The VLM layers replace the traditional patch merging layers in the SWIN transformer. These layers concatenate features of neighboring patches and aggregate spatial information into higher-level features. To ensure that the feature reduction aligns with the prompt, a cross-attention layer is introduced before the projection layer, enabling downsampling to be conducted relative to the prompt. A frozen language encoder generates a context-aware representation of the prompt, which is then used in the cross-attention layer to guide the encoding of visual features. The pre-training scheme for VisFocus involves two main stages: the Learn-to-Read LTR stage and the LMPM stage. In the LTR stage, the model is trained to predict the sequence of words in the document and their order of appearance, equipping the model with basic reading skills. This stage aligns with previous OCR-free literature and involves predicting the words in the document supervised by external OCR annotations. The LMPM stage builds on this by randomly sampling a local span of tokens and applying a masked language modeling task to this span. This stage explicitly guides the vision encoder to focus on the most relevant text patches, enhancing its ability to discern contextually relevant information associated with the language prompt. The experimental setup for VisFocus includes training on high-resolution input images and using a small multi-layer perceptron to align the output visual features with the language model. The models are pre-trained and fine-tuned on various VDU benchmarks, including DocVQO, InfoQO, ChartQA, OCR-VQA, and AI2D. The results demonstrate that VisFocus outperforms previous OCR-free methods, achieving state-of-the-art performance on multiple benchmarks. An ablation study is conducted to break down the contributions of VisFocus main components. The study shows that both the VLM layers and the LMPM pre-training stage contribute significantly to the performance gains. The VLM layers improve the model's attention towards patches relevant to the input prompt, while the LMPM stage enhances the model's ability to focus on specific parts of the text. The combination of these components results in a synergistic effect, leading to superior performance compared to the baseline models. Qualitative analysis further demonstrates VisFocus' ability to accurately answer questions on denser documents compared to baseline models. The model's attention maps reveal a focused attention on relevant words, showcasing its improved ability to extract contextually relevant information. The analysis of document density shows that VisFocus performs better on denser documents where focusing on relevant text patches is more significant. In conclusion, VisFocus represents a significant advancement in OCR-free VDU by integrating user prompts directly into the vision encoding process. The introduction of VLM layers in the LMPM pre-training task enables the model to focus on relevant text patches, leading to improved performance and efficiency in extracting information from dense documents. The research highlights the potential for further improvements through additional prompt-aware pre-training tasks and the application of VisFocus to other domains beyond text-rich documents. The paper Visual Text Generation in the Wild delves into the challenging task of generating high-quality text images within real-world scenes. The authors identify 3 critical criteria for successful visual text generation: fidelity, reasonability, and utility. Fidelity requires the generated text to be photorealistic and free from artifacts, with the text content accurately matching the specified conditions. Reasonability necessitates that the generated text regions and contents should naturally fit within the scene's context. Utility implies that the generated text images should enhance the performance of tasks like text detection and recognition. Existing methods for visual text generation can be broadly categorized into rendering-based and diffusion-based approaches. Rendering-based methods involve 3 main steps: identifying suitable text regions using feature maps, selecting text contents randomly from a corpus, and applying manually defined rules across various materials to render text onto background images. These methods, while useful for training optical character recognition OCR models, often lack fidelity and reasonability due to imprecise text region identification, nonsensical text contents, and noticeable rendering artifacts. Diffusion-based methods, on the other hand, directly generate images through models like Stable Diffusion, integrating text and background more seamlessly. However, these methods often suffer from limited diversity in text regions and scales, and the generated texts may not always align accurately with specified conditions. To address these limitations, the authors propose a novel method called CNVTGG, which follows a 2-stage paradigm. The first stage involves the text region and content generator TRCG, which leverages multimodal large language models LLMs to recommend suitable text regions and contents across multiple scales and levels. TRCG generates text regions and contents in a course-defined mechanism, starting with key points for text placement and refining them into detailed text regions and contents. The second stage involves the Local Visual Text Renderer LVTR, a conditional diffusion model that uses the recommendations from TRCG to generate high-quality text images. LVTR constructs image-level and embedding-level conditions to generate local text regions with consistent backgrounds, embedding them into the entire image for realistic scene text image generation. The paper highlights the significant advancements in scene text research, emphasizing the importance of synthetic data due to the high cost and difficulty of obtaining sufficient real-world data. The proposed CNVTG method is designed to synthesize photorealistic scene text images suitable for real-world scenarios. To train their models, the authors contribute a new dataset called SceneFTG-Erase, which contains 155,000 scene text images and their text erased backgrounds with detailed OCR annotations. Extensive experiments demonstrate that SceneFTG outperforms traditional rendering-based and recent diffusion-based methods in terms of fidelity, reasonability, and utility. SceneFTG-generated images are more realistic, with accurately integrated text and background, and provide superior utility for text detection and recognition tasks. The authors conduct detailed experiments to evaluate the performance of SceneFTG across different scales of text regions and provide a comprehensive ablation study to analyze the contributions of different components and design choices within the TRCG and LVTR models. The TRCG is fine-tuned using the pre-trained Lava-V1.5-7b model on the SceneFTG erase dataset. This involves training the visual encoder projection layer and the large language model using LoRa with a learning rate of 2e-5. The TRCG model is fine-tuned for 16 epochs with a batch size of 16, requiring 1 day of training on 4 Tesla AHAPA 100 GPUs. The LVTR is implemented based on the DAL2 model without pre-trained weights. The LVTR is trained on the SceneFTG erase dataset for 100 epochs using 4 Tesla AH 100 GPUs, with a learning rate of 1e-5 and a batch size of 96. The local region size is set to 64x512, and drop ratios of 50% and 20% are used for image embedding and text embedding, respectively. The experiments involve evaluating the fidelity of the generated images using metrics like freshet inception distance feed OCR detection and recognition metrics including F-score and line accuracy. SceneFTG is the best performance across these metrics, with visualizations demonstrating that SceneFTG-generated text is more accurately placed and integrated with the background, exhibiting fewer artifacts and errors compared to other methods. For the reasonability of generated text regions and contents, the authors use metrics such as intersection over union IO, PD edge, and clip score. SceneFTG outperforms other methods significantly in these metrics, generating text regions and contents that are contextually appropriate and fit naturally within the scenes. Visual comparisons show that SceneFTG avoids generating text in unreasonable regions, produces curved text regions to adapt to annular areas, and arranges multiple text regions within a holistic layout, resulting in more reasonable arrangements. The utility of SceneFTG is evaluated by training OCR models using the generated images and comparing the performance on text detection and recognition tasks. SceneFTG-generated samples achieve the best performance on all evaluation sets, demonstrating the ability to produce valid image samples that better simulate real-world scenarios. The authors also conduct a detailed ablation study to analyze the role of fine-tuning the visual encoder, the necessity of two-step generation in TRCG, the importance of region masks and auxiliary losses in LVTR, and the choice of hyperparameters. In conclusion, SceneFTG addresses the challenges of visual text generation by combining the strengths of LLMs and diffusion models, offering significant improvements in fidelity, reasonability, and utility over traditional methods. The authors acknowledge the limitations of their current work, including the relatively single and uncontrollable text colors and fonts in the generated images, and outline future research directions such as enhancing text diversity, adding multi-language support, and developing an end-to-end pipeline. The research paper titled Jumping Ahead, Improving Reconstruction Fidelity with JumpReLU Sparse Autoencoders explores enhancements in the field of Sparse Autoencoders Cs aimed at balancing the twin objectives of sparse sparsity and fidelancing the twin objectives of sparsity and fidelity in language model activations. Sparse autoencoders are an unsupervised learning approach that seeks to identify causally relevant and interpretable features in the activation space of language models LMS. The primary challenge addressed in this paper is the inherent tension between achieving high sparsity and maintaining high fidelity in the reconstruction of activations. The authors introduced JumpReLU SAYS, a modification of the traditional ReLU-based SAYS. The JumpReLU activation function includes a discontinuous jump that zeroes out pre-activations below a positive threshold, thus reducing false positives and improving the fidelity of sparse representations. This innovation is designed to provide state-of-the-art reconstruction fidelity at given sparsity levels, surpassing recent advances like gated and talk SAYS. To understand the context and significance of this work, it's important to grasp the role of SAYs in mechanistic interpretability. SAYs decompose the activations of language models into sparse linear combinations of feature directions from a large dictionary. The goal is to achieve decompositions that are both sparse, using only a few dictionary elements to reconstruct any given activation, and faithful, minimizing the approximation error between the original activation and its sparse reconstruction. The authors highlight that these two objectives are naturally in conflict. Increasing sparsity often results in decreased reconstruction fidelity. Previous research has focused on developing SAY architectures and training methods that improve this balance. Common approaches have involved introducing thresholding or gating operations to determine which features are used in the decomposition. JumpReLU SAYs represent a small but significant modification of the original ReLU-based SAY architecture. By replacing the ReLU activation function with the JumpReLU function, which zeroes out pre-activations below a certain threshold, the authors achieve better control over sparsity without compromising fidelity. The JumpReLU function is designed to maintain feature magnitudes above the threshold unaffected, thereby minimizing false positives and improving fidelity. Training JumpReLU SAYs involves using straight-through estimator STs to handle the discontinuity introduced by the JumpReLU function. The loss function used includes an L2 reconstruction error term and an L0 sparsity penalty, avoiding the limitations of training with L1 penalties which can shrink feature magnitudes and harm fidelity. The L0 penalty directly penalizes the number of non-zero features, ensuring true sparsity. The authors evaluate JumpReLU SAYs by comparing them with gated and top SAYs on the Gemma 29 billion language model activations. They measure reconstruction fidelity and sparsity across multiple layers and types of activations, including residual stream, MLP output, and attention output activations. The results demonstrate that JumpReLU SAYs consistently provide more faithful reconstructions at given sparsity levels than gated SAYs, and their performance is at least on par with, if not better than, top SAYs. A significant finding is that JumpReLU SAYs have more features that activate frequently compared to gated SAYs, which can impact interpretability. However, manual and automated interpretability studies show that JumpReLU features are similarly interpretable to those from other SAYs. The manual study involved human raters assessing feature interpretability, while the automated study used a language model to predict feature activations and correlate them with ground truth. The paper also delves into the technical aspects of training with STs. STs allow the training process to estimate gradients of the expected loss despite the piecewise constant nature of the loss function with respect to the threshold parameter. This involves using kernel density estimation (KDE) techniques to estimate probability densities and gradients, enabling effective training of the JumpReLU SAYs. The research acknowledges certain limitations. The evaluations are primarily conducted on a single model, Gemma 29 billion, which raises questions about the generalizability of the results to other models. Moreover, the current measures of feature interpretability may not fully capture the attributes that make SAYs useful for downstream tasks. Further research is needed to develop more comprehensive evaluation metrics and validate the findings on different models. The paper concludes that JumpReLU SAYs offer a mild improvement over existing SAY training methodologies, providing better reconstruction fidelity without compromising interpretability. The authors suggest that future work could focus on reducing the prevalence of high-frequency features and exploring more principled ways to select hyperparameters like the threshold and KDE bandwidth. The ST approach introduced is general and opens up possibilities for training SAYs with other discontinuous loss functions that could further improve their quality and usability. In summary, this paper presents a thorough and detailed exploration of JumpReLU SAYs, providing significant advancements in the balance of sparsity and fidelity in language model activations. The innovative use of the JumpReLU activation function in STs for training represents a noteworthy contribution to the field, with promising implications for future research and applications in mechanistic interpretability and beyond. SciCode, a research coding benchmark curated by scientists, is a benchmark designed to evaluate the capabilities of language models LMS in generating code for solving scientific research problems. This benchmark is curated by scientists and incorporates input from experts across 16 diverse natural science subfields, including mathematics, physics, chemistry, biology, and materials science. The motivation behind developing SciCode stems from the need for challenging, high-quality, and realistic evaluations of LMS, which have now begun to outperform average humans in many tasks. Existing benchmarks often fail to keep pace with the advancements in LM performance, leading to discrepancies between the perceived and actual capabilities of these models. Therefore, there is a pressing need for a benchmark that accurately reflects real-world applications and assesses the practical performance of LMS in scientific coding. SciCode is structured around 80 main problems, each of which is decomposed into multiple subproblems, totaling 338 subproblems. These problems are designed to factorize naturally into subproblems that involve knowledge recall, reasoning, and code synthesis. Each problem comes with optional scientific background information, scientist-annotated gold standard solutions, and test cases for evaluation. The problems are sourced from various natural science fields, ensuring a comprehensive representation of the sciences where extensive code development is essential. The design principles of SciCode include an intentional focus on natural science fields such as computational mechanics, quantum information and computing, quantum chemistry, ecology, and molecular modeling. The benchmark emphasizes high annotation quality, with all problems annotated, revised, and verified by at least 2 senior researchers. The problems are realistic and current, sourced from scientists' everyday research tasks or influential papers, ensuring relevance to real-world applications. SciCode also addresses data contamination by curating problems that have zero overlap with publicly available datasets. The problems are designed to test the comprehensive and all-around capabilities of LMS, requiring deep scientific background knowledge, strong analytical skills, and the ability to integrate partial solutions into a complete one. The benchmark also provides opportunities to evaluate various model capabilities in different setups by toggling options such as providing scientific background information or conditioning on gold or generated solutions to previous subproblems. SciCode offers a challenging evaluation for current LMS. The best performing model among those tested, Claude 3.5-Sonnet, could solve only 4.6% of the problems in the most realistic evaluation setup. This indicates that SciCode is a difficult benchmark for current LMs, which struggle to solve main problems despite being able to solve some subproblems correctly. Providing scientific background knowledge substantially improves model performance, highlighting the model's lack of inherent knowledge and reasoning capabilities in these natural science fields. The evaluation design of SciCode involves numerical tests that list input-output pairs to check if the generated code produces the same outputs as the ground truth. Domain-specific test cases are also introduced to evaluate whether model-generated solutions align with scientists' practical needs and further ensure the correctness and applicability of each solution within its specific field. These tests are extracted from real scientific workflows and are used to verify code accuracy by reproducing results published in academic papers or matching analytical solutions derived from theoretical models. The data annotation process consists of 3 main stages: problem selection, evaluation design, and problem validation. In the problem selection stage, scientists select problems that require intense scientific knowledge and reasoning to optimally test the LMS scientific capabilities. This ensures that both the breadth and depth of frontier research are addressed. The evaluation design stage involves designing both numerical and domain-specific test cases to ensure the problem's validity. The problem validation stage involves 3 rounds of validation and revision to ensure that the problems are scientifically rigorous, clear, and unambiguous. SciCode also facilitates various types of evaluations, such as evaluating models with and without scientific background knowledge and using gold or generated solutions to previous subproblems. These different setups allow for a comprehensive assessment of the model's coding capabilities and their ability to follow instructions and integrate partial solutions into complete ones. In summary, SciCode is a well-designed benchmark that provides a challenging and realistic evaluation of language models' capabilities in generating code for scientific research problems. It aims to drive the development of new AI methods for accelerating scientific research by providing a comprehensive and high-quality evaluation framework. The benchmark covers diverse natural science fields and emphasizes high annotation quality, realistic problems, and rigorous validation processes to ensure the relevance and accuracy of the evaluations. The paper Fast Matrix Multiplications for Lookup Table-Quantized LLMs addresses the significant latency challenges in deploying large language models LLMs due to memory bandwidth constraints, particularly during generative token-by-token inference. The primary bottleneck is the transfer of model parameters from the GPU's global memory to its registers. Weight-only quantization, which compresses model parameters to lower precision, helps to reduce memory movement and improve latency. However, developing high-performance kernels for weight-quantized LLMs is challenging, especially when the weights are compressed to non-evenly divisible bit widths, such as 3 bits, with non-uniform lookup table quantization. To tackle these challenges, the authors introduce Flute Flexible Lookup Table Engine, which optimizes weight-quantized LLMs through a combination of offline weight restructuring to minimize bit manipulations associated with unpacking, vectorization, and duplication of the lookup table to mitigate shared memory bandwidth constraints. The paper claims that Flute can be 2 to 4 times faster than existing GEM kernels at batch sizes less than 32 and quantization group sizes of 128, typical in LLM inference. Additionally, they apply Flute to quantize the Llama 3 model to various configurations, achieving competitive quantization performance against strong baselines while obtaining an end-to-end throughput increase of 1.5 to 2 times. The paper begins by providing background information on GPU architecture and memory bandwidth bottlenecks. GPUs are massively parallel processors designed for throughput-oriented workloads with large amounts of independent work. Current generation NVIDIA GPUs consist of an array of many individual streaming multiprocessors (SMS), each with its own set of warp schedulers and a shared memory scratchpad accessible to all schedulers. The warp schedulers execute instructions on their functional units, operating in a SIMD fashion over vectors of 32 data elements at a time. CUDA programming allows programmers to work at the level of individual logical threads executing scalar operations, implicitly organizing every group of 32 consecutive threads into a single warp, corresponding to the GPU hardware's native unit of instruction execution. Although GPUs can execute large numbers of instructions in parallel, the rate at which instructions are executed is not always the bottleneck in realistic GPU workloads. Instead, the maximum achievable throughput of a GPU workload is often constrained by the speed of data movement between levels of the GPU's memory hierarchy. The memory resources of modern NVIDIA server-class GPUs consist of tens of gigabytes of off-chip DRAM global memory, tens of megabytes of on-chip SRAM L2 cache accessible to all SMS, hundreds of kilobytes of local SRAM per SM split into L1 cache and a local scratch pad, and hundreds of kilobytes of local SRAM per SM acting as registers for the threads running on that SM. The read-write bandwidth of these memory resources can easily become the limiting factor for realistic GPU workloads. The authors explain that LLMs can be either compute-bound or memory-bound depending on the context. During training, large prefill and large batch inference, high arithmetic intensity saturates compute throughput due to large matrix sizes and matrix multiplications matmuls. However, token-by-token inference involves narrower matmuls due to smaller batch dimensions, resulting in low arithmetic intensity. Reducing memory operations in such cases can enable practical speedups, even if the number of floating-point operations flops remains the same or increases slightly. The paper then delves into the quantization of LLMs, distinguishing between uniform and non-uniform quantization. Uniform quantization converts a group of full precision weights to lower precision intervals of equal size, allowing for the use of integer matrix multiplications to enable speedups beyond the savings from reduced memory movement. However, activation quantization remains difficult due to outlier channels, necessitating sophisticated mitigation strategies. Weight-only quantization, which involves quantizing only the weights, remains popular for LLMs as it reduces quantization error further by applying quantization at a more fine-grained level. Non-uniform quantization generalizes uniform quantization by mapping weights to potentially unequal intervals, with lookup table quantization being a flexible variant that maps intervals to arbitrary values via a lookup table. The core of the paper is the introduction of the Flute kernel, designed to address the challenges of weight-quantized LLMs. Flute combines offline weight restructuring, vectorized lookups in shared memory, and Stream-K workload partitioning. Offline matrix restructuring leverages the static nature of quantized weights during inference to reorder weights such that after dequantization, the weights are already laid out in the required format, avoiding runtime data reordering. Vectorized lookup in shared memory reduces memory access instructions by creating an alternative lookup table that holds pairs of values, allowing simultaneous lookup of two values and reducing bank conflicts in shared memory. Stream-K workload partitioning distributes the workload across SMS more evenly, mitigating wave quantization by decomposing the work at a finer granularity and enabling multiple SMS to collaborate on computing a single output tile. The experimental results demonstrate the effectiveness of Flute. The authors compare Flute against existing mixed-input MATML kernels and show that Flute achieves favorable performance across a wide range of matrix shapes on both a 6000 and 100 GPUs, occasionally nearing the peak theoretical speedup. Flute's flexibility is showcased by experimenting with different group sizes, bit widths, and group sizes, consistently achieving speedups over torch.mm across a wide range of settings. End-to-end evaluations on Llama 3 models show that Flute achieves competitive quantization performance while increasing throughput by 1.5 to 2 times. The authors conclude by discussing the potential of Flute to enable researchers and practitioners to explore new quantization algorithms that can learn better lookup tables. They highlight the main challenges in developing fused quantized matrix multiplication kernels, such as the lack of hardware support for mixed-type instructions and in register dynamic indexing. They suggest that native support for such instructions in future hardware could be beneficial, as well as enhanced hardware acceleration for indexing into small lookup tables. Overall, the paper presents Flute as a significant advancement in optimizing weight-quantized LMS, addressing key challenges in matrix multiplication, and demonstrating substantial performance improvements in both kernel-level benchmarks and end-to-end LLM workloads. The detailed methodologies, experimental results, and discussions provide a comprehensive understanding of Flute's capabilities and potential applications in enhancing LLM deployment efficiency. The research paper focuses on the development and safety alignment of the Phi-i3 series of small language models LLMs by Microsoft. These models are designed to be computationally efficient, capable of running on devices with limited resources such as smartphones. The Phi-3 series includes models like Phi-3 Mini 3.8 billion parameters, Phi-3 Small 7 billion parameters, and Phi-3 Medium 14 billion parameters. Despite their smaller size, these models demonstrate competitive performance on various benchmarks. The main goal of the paper is to ensure that these models are aligned with human preferences and safety considerations through a methodical and iterative process known as the break-fix cycle. Recent innovations in language model training have shown that it is possible to create highly performant small language models LLMs by training them on curated and synthetic datasets. The Phi-3 models, particularly Phi-3 Mini, can achieve significant performance metrics such as 69% on the Massive Multitask Language Understanding MLU benchmark and 8.38 on the MT bench, making them competitive with larger models like Mixtral 8x7 billion and GPT-3.5. These open-source LLMs enable various on-device generative AI applications, underscoring the importance of aligning these models with safety and human preferences as they are deployed in numerous domains. The safety alignment of the Phi-3 models involves an iterative break-fix cycle consisting of 5 main stages: safety dataset curation, safety post-training, quantitative and qualitative responsible AI array evaluations, AI red teaming, and vulnerability identification. This cycle is repeated multiple times to fine-tune the models, aiming to generate safe responses across different contexts. The safety alignment approach begins with safety dataset curation, where existing publicly available datasets are utilized and modified as needed. Additional datasets are generated based on feedback from the AI Red team, which is an independent group focused on probing the models for harmful content. These curated datasets are then used in the safety post-training stage, where they are mixed with standard preference datasets during supervised fine-tuning SFT and direct preference optimization DPO. Quantitative and qualitative RAI evaluations are conducted to select release candidates for further testing. These evaluations involve a wide spectrum of benchmarks and metrics to assess the safety and performance of the models. The selected release candidates are then shared with the AI Red team, which employs various adversarial techniques to test the models for harmful content. This red teaming strategy includes single-turn and multi-turn prompts, as well as encoded prompts and advanced strategies like crescendo, which gradually escalates the conversation to attempt to jailbreak the model. The paper details the safety post-training process, which involves using a combination of open source and in-house datasets. The open source datasets are improved by regenerating responses with GPT-4 and applying specific instruction conversion methods. In-house datasets are curated to address specific risks identified by the AI Red team. These datasets are used in both the SFT and DPO stages, and safety evaluations are conducted at each model checkpoint to decide which models to further review and eventually release. Red teaming plays a crucial role in the safety alignment process. The AI Red team independently tests the models using different adversarial scenarios to identify potential risks. These scenarios are divided into low-skilled and intermediate adversary personas. A low-skilled adversary represents a typical user who directly asks for harmful content, while an intermediate adversary attempts to subvert the model's safety guardrails using techniques like encoding prompts and known jailbreak methods. The AI Red team uses a tool called Pirate Python Risk Identification Toolkit to automate prompt generation, conversion, response scoring, and multi-turn conversations driven by an attacker language model. Safety evaluations are an essential part of the alignment process. Microsoft's internal automated measurement system leverages advanced models like GPT-4 to simulate multi-turn conversations between adversarial AI agents and the target model. This system evaluates the models across 5 scenarios grounding third-party content, harmful content continuation, harmful content summarization, and jailbreak attempts. The results are measured in terms of ungroundedness, severity of harm, and defect rates, with lower scores indicating better performance. The XDIS benchmark evaluates the models on a public dataset of safe and unsafe prompts. It measures the inappropriate prompt refusal rate IPRR and valid prompt refusal rate VPRR, reflecting the model's ability to handle harmful and harmless prompts appropriately. The Decoding Trust benchmark assesses the model's trustworthiness across various metrics such as stereotype bias, adversarial robustness, out-of-distribution robustness, privacy, machine ethics, and fairness. These metrics help evaluate the model's understanding of responsible AI risks. The Toxygen benchmark focuses on detecting harmfulness in prompts, particularly adversarial and implicit hate speech. The Phi-3 models are evaluated on this benchmark, and their performance is compared with other models like Mistral and Gemma. The iterative safety alignment approach significantly reduces the generation of harmful content. Multiple rounds of the break-fix cycle are necessary to identify and mitigate a realistic range of real-world risks. The results show a 75% reduction in harmful content generation after several iterations. The paper also discusses responsible AI considerations for developers. It emphasizes the importance of adapting models with further fine-tuning and safety measures for specific use cases. Developers are encouraged to use safety classifiers, prompt engineering techniques, and provide guidance to end users on interpreting model outputs. The common limitations of language models such as biases, inappropriate content, unreliable information, and limited scope for code are highlighted. Developers should consider these limitations and implement appropriate safeguards in high-risk scenarios. In conclusion, the paper presents a comprehensive approach to safety aligning the Phi-3 series of language models using an iterative break-fix cycle. This method significantly reduces harmful content generation and ensures the models align with human preferences and safety considerations. However, the models still have fundamental limitations common to modern language models. The paper encourages developers to consider additional safety measures and responsible AI practices for their specific use cases, promoting the development and deployment of safe and trustworthy AI systems. The paper titled SparseCraft Few-Shot Neural Reconstruction through Stereopsis Guided Geometric Linearization presents a novel approach to 3D shape recovery and view-dependent appearance synthesis from a few colored images, enabling efficient 3D reconstruction and novel view synthesis. The method, named SparseCraft, learns an implicit neural representation using a signed distance function SDF and a radiance field. The model is trained progressively through ray marching-enabled volumetric rendering and regularized with learning-free multi-view stereo MVS cues. A key contribution is a new implicit neural shape function learning strategy that encourages the SDF field to be as linear as possible near the level set, thus making the training robust against noise from the supervision and regularization signals. SparseCraft achieves state-of-the-art performance in novel view synthesis and reconstruction from sparse views, requiring less than 10 minutes for training. The introduction highlights the importance of digital replication of the 3D world, which has numerous applications in computer vision and graphics. Current solutions often require high-quality or abundant input data, which is not always feasible in constrained scenarios. SparseCraft aims to capture both the shape and appearance of objects or scenes from a few images, seeking metrically accurate 3D reconstruction and photorealistic novel view synthesis. Traditional computational photogrammetry methods like structure from motion SFM and multi-view stereo MVS can lead to noisy and incomplete meshes in challenging scenarios. In contrast, implicit neural representations INR have shown the ability to learn detailed shapes and radiance through image-supervised differentiable volumetric rendering from dense image arrays. However, learning accurate implicit shape representations is challenging with only a few images. The paper then discusses related work, categorizing it into multi-view stereo MVS and implicit neural representations INR. Conventional MVS can be volumetric, point cloud, or depth map based. Depth map-based methods are preferred due to their versatility, dividing the problem into depth map estimation and fusion stages. Implicit neural fields use deep neural networks to model 2D or 3D data as continuous functions, overcoming limitations of explicit ones like meshes and point clouds. The seminal work on neural radiance fields NERF combines volume rendering and implicit representations, enabling learning diverse tasks, including novel view synthesis, 3D generation, and video rendering. Despite improvements, challenges like geometric bias and training time remain. The methods section explains how SparseCraft achieves 3D reconstruction and novel view synthesis by learning implicit shape and radiance functions simultaneously. The shape is modeled using an SDF parameterized with a neural network, while radiance is modeled as a view direction and location-dependent color function. The inferred shape can be obtained at test time as the zero-level set of the learned SDF. A novel image can be generated through ray-wise volumetric rendering per pixel using the converged neural SDF and radiance fields. Learning implicit neural shape and radiance involves the NERF framework, which uses volumetric scene representation through a synthesis and compare procedure between generated and ground truth pixel values. The color of a pixel corresponding to a ray is generated through integration along the ray, with volume density representing differential opacity and transparency representing accumulated transmittance. This approach is improved by involving a function that transforms the SDF into density for volumetric rendering. Regularization with Stereopsis cues is crucial for learning an SDF and radiance field from few images. Automatic calibration preprocess estimates camera intrinsic and extrinsic parameters, essential for 3D consistent volumetric rendering and ray marching. Qalam is used to acquire dense fused MVS point cloud, point-wise normal estimations, and color labels using sparse input images. MVS points have been exploited before in learning NERFs and SDF-based radiance from images, but SparseCraft uses these cues in learning SDF-based radiance in the sparse setting. The paper introduces a novel strategy to address noise challenges by focusing on the level set of the SDF, encouraging it to be as linear as possible to avoid overfitting on noisy samples. The implementation builds on the instant NSRPL implementation of LazyLLM, utilizing NERFAC's accelerated sampling with an occupancy grid. The SDF consists of a multi-resolution hash encoding followed by a small MLP, and the radiance network consists of two small MLPs. An explicit occupancy grid guides sampling along rays for inference, enabling fast training. Progressive learning through positional encoding or learnable features is employed, reducing overfitting and improving training stability and rendering quality. Experimental results show that SparseCraft outperforms state-of-the-art methods in novel view synthesis and reconstruction tasks across various datasets, including DTU, BlendNVs, and Tanks temples. The method is faster and produces more detailed and complete surfaces compared to previous methods. Qualitative and quantitative comparisons demonstrate superior performance in handling challenging surfaces and providing photorealistic renderings. The paper also includes an ablation study to assess the contributions of different components of SparseCraft. The Taylor losses for geometric regularization outperform direct MVS supervision, and the progressive hash encoding improves surface quality and rendering stability. Regularizing the diffuse component of the color network with MVS color labels enhances rendering results. In conclusion, SparseCraft provides an efficient and robust solution for 3D reconstruction and novel view synthesis from sparse input images, bridging the gap between traditional photogrammetry and deep learning-based methods through innovative regularization strategies. The method addresses the challenges of minimal input scenarios, offering a significant contribution to the field of 3D capture. PlacidDreamer advancing harmony in text to 3D generation. The task of generating 3D assets from text, known as text to 3D generation, has garnered significant attention for its potential to simplify the creation of 3D models, a process that traditionally requires specialized knowledge. The scarcity and lower quality of 3D data compared to 2D data make it challenging to develop high-quality 3D models directly. A promising approach to overcome this challenge involves adapting pre-trained 2D models for 3D generation. One dominant method in this field is optimization-based, leveraging score distillation algorithms that distill generative capabilities from pre-trained 2D fusion models to guide subsequent 3D generations. Recent methods for text to 3D generation typically utilize end-to-end 3D generation models to initialize 3D Gaussians, multi-view diffusion models to enforce multi-view consistency, and text-to-image diffusion models to refine details with score distillation algorithms. However, these methods face two primary limitations: conflicts in generation directions and issues with oversaturation and score distillation. The conflicts arise because different models aim to produce diverse 3D assets, leading to contradictory optimization directions. The problem of oversaturation and score distillation has not been thoroughly investigated and solved, resulting in discrepancies in color distribution between the 3D content created and the 2D images generated by diffusion inference processes. To address these limitations, we propose PlacidDreamer, a text-to-3D framework that harmonizes initialization, multi-view generation, and text condition generation with a single multi-view diffusion model. PlacidDreamer also employs a novel score distillation algorithm to achieve balanced saturation. To unify the generation direction, we introduced the Latent Plane module, a training-friendly plugin extension that enables multi-view diffusion models to provide fast geometry reconstruction for initialization and enhance multi-view images to personalize the text-to-image diffusion model. To address the oversaturation problem, we view score distillation as a multi-objective optimization problem and introduce the balanced score distillation algorithm, which offers a Pareto optimal solution that achieves both rich details and balanced saturation. The Latent Plane module is designed to be training efficient and adaptable to various multi-view diffusion models, accommodating different viewpoint configurations. It enhances the multi-view diffusion model by enabling fast geometry reconstruction and improving its capabilities in generating multi-view images. The reconstructed geometry is then utilized to initialize 3D Gaussian points, and the improved multi-view images are used to personalize the text-to-image diffusion model with directional prompts. This coordinated approach aligns the generation directions within the pipeline with the outcomes from the multi-view diffusion model, promoting convergence and significantly enhancing the quality of the generated content. To delve into the causes of oversaturation, we decompose the score distillation equation into two primary components: classifier guidance and smoothing guidance. Prior algorithms have suffered from an imbalance where classifier guidance overwhelmingly dominates smoothing guidance, leading to prevalent oversaturation. Our analysis reveals that in over 30% of instances, the optimization directions of these two guidances form obtuse angles, resulting in negative optimization along certain directions with a fixed classifier-free guidance parameter. making it challenging to maintain control over balance after multiple optimization steps. To rectify this imbalance, we propose to treat score distillation as a multi-objective optimization problem and introduce a balanced score distillation algorithm. This algorithm incorporates a multi-objective optimization solution, the multiple gradient descent algorithm, which dynamically adjusts the optimization directions to converge at Pareto optimal points, where the generated results exhibit both rich details and balanced saturation. Extensive experiments validate the outstanding capabilities of PlacidDreamer. Quantitative evaluations conducted on the T3 benchmark reveal that PlacidDreamer consistently outperforms baseline methods by a margin of at least 5 points in both generation quality and alignment metrics. Qualitative comparisons show that PlacidDreamer produces high-fidelity 3D models with balanced saturation and rich details. Furthermore, ablation studies evaluate the contribution of each proposed module to the overall quality. The latent plane module, by providing fast geometry reconstruction and enhancing multi-view image generation, plays a crucial role in the framework. The balanced score distillation algorithm effectively addresses the oversaturation problem, ensuring a balanced generation process. To implement the latent plane module, we follow a specific strategy within the UNet architecture, which is commonly used in multi-view diffusion models. We select the feature map with the highest resolution and the smallest index as it encompasses the deepest and most intricate features extracted by the model, containing comprehensive geometric information. At each time step during the reverse diffusion process, we obtain multiple feature maps from different viewpoints. For every point in the 3D space, we project it onto each feature map and derive its corresponding feature through trilinear interpolation. We then apply an additional linear layer to extract low-dimensional features from the extracted features. To better represent the features of a spatial point, we concatenate each feature with its respective camera embeddings and coordinate embeddings. For the sigma token corresponding to obtaining volume density, we concatenate a trainable embedding with embeddings of the time step, followed by a linear layer. These tokens, along with multi-view features, undergo mutual enhancement through attention layers. The volume density value is obtained using a multi-layer perceptron on the enhanced sigma token. The multi-view enhanced feature tokens are used for volume rendering to gather features enhanced on the object surface. The enhanced feature map is added to the original feature map, continuing to function in the decoder of the diffusion model, ultimately producing the model's predicted noise, which is then integrated into diffusion training and inference. Training the latent plane module involves 2 stages. In the first stage, we independently train the volume density generation module, enabling the selection of arbitrary camera viewpoints. Subsequently, we calculate the depth of each spatial point relative to the selected camera. After volume rendering, we supervise the generated occupancy and depth maps. In the second stage, we train the feature map augmentation using the standard diffusion loss. The balanced score distillation algorithm is a novel approach to score distillation. By viewing score distillation as a multi-objective optimization problem, we address the imbalance between classifier guidance and smoothing guidance. The algorithm employs the multiple gradient descent algorithm to dynamically adjust optimization directions, ensuring that each optimization step is non-negative in both directions, avoiding oversaturation. This approach finds Pareto optimal points where the generated results exhibit both rich details and balanced saturation. In conclusion, PlacidDreamer represents a significant advancement in text-to-3D generation. It addresses critical challenges of conflicting optimization directions and oversaturation in score distillation. By harmonizing initialization, multi-view generation, and text condition generation with a single multi-view diffusion model, and employing the balanced score distillation algorithm, PlacidDreamer achieves high-fidelity 3D content with controlled color saturation and rich details. This framework sets a new benchmark for future research in the field of text-to-3D generation. The research paper titled Qalam, a Multimodal LLM for Arabic optical character and handwriting recognition addresses the significant challenges posed by Arabic optical character recognition OCR and handwriting recognition HWR. The Arabic script's cursive and context-sensitive nature complicates the design of robust OCR models. The study introduces Qalam, a novel foundation model built on a SWINV2 encoder and Roberta decoder architecture which significantly outperforms existing methods. Qalam achieves a word error rate of just 0.80% in HWR tasks and 1.18% in OCR tasks. The model is trained on a diverse dataset, including over 4.5 million images from Arabic manuscripts and a synthetic dataset comprising 60,000 image-text pairs. Notably, Qalam demonstrates exceptional handling of Arabic diacritics, a critical feature in Arabic scripts. It also shows a remarkable ability to process high-resolution inputs, addressing a common limitation in current OCR systems. These advancements underscore Qalam's potential as a leading solution for Arabic script recognition, offering a significant leap in accuracy and efficiency. Optical character recognition (OCR) technology has revolutionized the way we interact with written and printed materials. It enables the conversion of various documents, including scanned paper documents, PDF files, or images captured by a digital camera, into editable and searchable data. The ability of OCR to digitize text has found applications in numerous domains ranging from banking and healthcare to education and historical research, among others. Arabic OCR and HWR pose substantial challenges due to several distinctive features of the Arabic script. The Arabic writing system is cursive and context-dependent, a characteristic that complicates the design of robust OCR models. Further intricacies such as diacritical marks, loops, overlaps, ligatures, dots, and multi-context joining contribute to the complexity of the task. In addition to these structural challenges, the vast diversity of Arabic fonts and individual handwriting styles further complicates character recognition and segmentation tasks. Finally, the lack of comprehensive and diverse annotated datasets increases the difficulty of Arabic OCR and HWR tasks. OCR systems can be classified based on the type of input data they process, handwritten or printed. In this paper, for clarity, printed text recognition is specifically referred to as OCR, although both types broadly fall under the OCR umbrella. The objective of this work is to tackle these complex tasks, making several key contributions that collectively underscore the novelty of the research. The first contribution is the introduction of Qalam, a novel OCR and HWR model specifically engineered for Arabic script, establishing a new state-of-the-art performance across diverse datasets. The second contribution is the compilation of a large and diverse collection of datasets and the introduction of the Midad benchmark for Arabic OCR and HWR. This will serve as a resource for future research in the community. The third contribution is an in-depth analysis of the inherent complexities associated with Arabic script OCR, contributing towards a broader understanding of the challenges in this domain. The fourth contribution is detailed comparative evaluations against multiple baselines, thus emphasizing the effectiveness of the approach. Traditional hidden Markov model (HMM) approaches in sequence modeling have been largely surpassed by deep learning techniques that do not require explicit segmentation. Connectionist temporal classification (CTC) models and encoder-decoder models with attention mechanisms represent two primary deep learning categories. Recent advances include transformer models and pre-trained models. Handwriting recognition (HWR) has evolved from HMMs to CTC-based models due to their accuracy without explicit segmentation. These models often use recurrent neural networks (RNNs) and their variations like long short-term memory (LSTM), bidirectional LSTM, BLSTM, and multidimensional LSTM, and combinations with convolutional neural network CNNs such as CNN-BLSTM. Recurrence-free models optimized with CTC using only CNNs have also been developed. OCR, divided into scene text recognition (STR), scan document OCR, and synthetic text OCR, has evolved from HMMs to pre-trained transformer models. RNN CTC-based models combine CNN and BLSTM models, and encoder-decoder architectures with attention mechanisms have been used. Recently, transformer-based models have gained prominence. Multimodal large language models (LLMs) have impacted tasks like visual question answering, VQA, and OCR-related tasks. Despite their success, challenges in text recognition within images remain due to lower encoder resolution. Open-source models like LaVar and MonkeyText are improving text recognition, while closed-source models like GPT-4v and Gemini Pro contribute to these advancements. Arabic, HWR, and OCR initially relied on HMMs. Later, CTC-based models with RNNs and CNNs replaced HMMs. An MDLSTM model was used for the CAT dataset, and a pure CNN model optimized with CTCC loss was introduced. Recent advancements include transformer models, though Arabic LLMs still face challenges in text recognition within images. The Medad benchmark comprises a variety of printed and handwritten Arabic OCR datasets. These include MadBase AHCD, ADAB Alexu Shutter PATSA 01, IDPL PFOD, UPTI, and OnlineCat, providing a broad and varied base for training and validating OCR models for Arabic and other closely related languages. In instances where the original datasets came pre-partitioned into standard training, development, and testing splits, these existing divisions were maintained to preserve the integrity of the original data structure. In the absence of such predefined splits, each dataset was randomly shuffled and split into 80% training, 10% development, and 10% testing sets. The Medad benchmark also includes in the wild Arabic OCR and HWR datasets such as CAT and historical manuscripts, which provide a comprehensive testbed for evaluating OCR models on more challenging and diverse Arabic text samples. To address the challenges of both Arabic HWR and OCR, the research employs a vision encoder-decoder VED framework that ingeniously brings together transformer-based models. This framework leverages the power of transformer-based vision models as encoders, adeptly processing image data, and pairs it with the linguistic sophistication of transformer-based language models as decoders. The result is a synergistic pairing that skillfully transcodes visual information into meaningful textual output, thus overcoming the intricate complexities of Arabic OCR. Various encoder and decoder combinations were extensively analyzed, investigating their implications for model performance. In VED design, the encoder ingests image data, while the decoder manages ground truth caption inputs via teacher forcing during training. Autoregressive training for the next token prediction is ensured using causal self-attention in the model. This mechanism restricts a token's attention only to its predecessors, maintaining the sequential nature of the input text. The encoder takes images resized to a fixed size, padded for uniformity, and partitioned into patches with a fixed size. These patches are subsequently flattened and linearly projected into dimensional vectors to form patch embeddings. The CLS token is retained to represent the image, and learnable 1D position embeddings based on absolute positions are incorporated. The decoder in the VED structure consists of layers identical to the encoder but with an additional encoder-decoder attention mechanism. It employs attention masking to prevent the model from peeping into the future during training. Its hidden states are projected linearly to the vocabulary size, and probabilities are computed using softmax. The cross-attention layer weights are randomly initialized when warm, starting from pre-trained transformer-based models. To provide a comparative analysis, a range of established OCR models were considered as baselines. These models, varying in complexity and technique, include CRNN, Gated CRNN, Beelstem CTC, Tesseract, and Troker. The CRNN model blends convolutional and recurrent layers, concluding with a linear layer and CTC loss function. It leverages dropout, batch normalization, LazyLLM, maxpool, and bidirectional 1D-LSTM layers. Data augmentation through random distortions is used for enhanced robustness. The gated CNN Beelstem CTC architecture includes gated CNNs for feature extraction. Convolutional layers, gates, bidirectional LSTM layers, and a linear layer compose the encoder-decoder structure. The model minimizes the CTC objective function using RMSprop and incorporates data augmentation. Tesseract is a versatile open-source OCR engine sponsored by Google, designed to be a universal text recognition tool recognizing over 100 languages. Tesseract works by decomposing the input image into lines and words. Troker is a text recognition model that uses pre-trained image and text transformer-based models. Pre-training on large-scale synthetic data and fine-tuning on human-labeled datasets make Troker effective in printed, handwritten, and scene text recognition tasks. The model performance is evaluated based on the word error rate WEIR, computed as the normalized Levenshtein distance at the word level. The experiments involved selecting the most suitable encoder from available options. Rigorous tests were conducted with 4 different encoders: VIT, DEET, BEAT, SWIN, and SWIN2 transformers, while keeping the XLM Roberta as the constant decoder. The D-encoder model exhibited superior results due to its adeptness at discerning text in various forms and orientations in images and recognizing intricate handwritten patterns. However, the SWINV2 encoder model also showed notable performance, particularly in line-level handwriting recognition on the OnLinCat dataset, due to its ability to handle variable image inputs. The results underline the effectiveness of both D8 and SWINV2 in handling diverse OCR and HWR tasks across MIDAD datasets. The paper titled Efficient Audio Captioning with Encoder-Level Knowledge Distillation addresses the significant advancements and increasing complexity in automated audio captioning AAC models. AAC is a task that generates textual descriptions from audio inputs, thereby bridging the audio and text modalities. Recent improvements in AAC performance have been substantial, but they often come at the cost of increased model complexity and computational demands, making them challenging to deploy on resource-constrained devices. To tackle this issue, the paper proposes a knowledge distillation KD framework for AAC, focusing specifically on the encoder component of encoder-decoder-based models. The study posits that it is more effective to distill knowledge into the encoder rather than the decoder. This approach involves incorporating an encoder-level KD loss into the training process alongside the standard supervised loss and sequence-level KD loss. The background of the study highlights that state-of-the-art AAC models typically employ deep convolutional neural network CNNs or transformers to extract embeddings from audio inputs and large-scale pre-trained transformer models for text generation. These large models, while achieving high performance, require substantial computational resources, memory, and storage. For instance, the HTSA-T-BART model contains about 170 million parameters and requires 160 gigafloat-point operations flops for inference on a 10-second audio clip. The complexity and size of such models pose significant challenges for deployment on devices with limited resources. Knowledge distillation is a technique used to compress large models into smaller, more efficient ones. This process involves training a small student model to mimic the behavior of a larger teacher model. The paper explores two methods for encoder-level KD mean squared error MSE loss and contrastive loss. The MSE loss aims to minimize the distance between the student and teacher audio embeddings, while the contrastive loss encourages the student encoder to distinguish between different audio clips by bringing embeddings of the same audio clip closer and pushing embeddings of different audio clips further apart. The proposed KD framework is designed to leverage the architecture flexibility offered by KD, allowing for the development of highly efficient student models regardless of the teacher's architecture. The study begins by analyzing the bottleneck of distilling the encoder-decoder captioning framework, revealing that a compact encoder results in a larger performance drop than a compact decoder. This insight leads to the emphasis on developing an efficient and effective encoder. The framework consists of a teacher model, which uses a SWIN transformer encoder and a BART decoder, and a student model, which uses EfficientNet B2 as the encoder and a shallow two-layer transformer as the decoder. This combination significantly reduces the number of parameters and computational requirements from 170 million to 11 million parameters. Encoder-level KD is a crucial aspect of the framework. It ensures that the student model generates embeddings that closely follow those of the teacher model. This is achieved through either MSE loss, which minimizes the L2 distance between the teacher and student embeddings, or contrastive loss, which uses cosine similarity to guide the student encoder in learning the same ability as the teacher to distinguish between different audio clips. To further enhance training, the paper incorporates unannotated audio data by using the teacher model to generate pseudo-caption labels. This approach allows the use of a larger dataset for training, which helps in scenarios with limited annotated data. The framework is evaluated on two datasets Clotho, a smaller dataset with around 6,000 audio clips, and audio caps, a larger dataset with over 50,000 audio text pairs. The entire audio set is used as audio-only data for training. The student model's audio encoder is pre-trained on audio set, while the transformer decoder is trained from scratch. The model is trained for 25 epochs with a batch size of 32, using a learning rate that linearly warms up initially and then exponentially decays. During inference, beam search with a beam size of 3 is used. The performance is evaluated using traditional metrics like Blue Rouge, Meteor, Cider, and Spice, as well as a more advanced model-based metric Fence, which correlates better with human judgments. Experimental results show that the student model, trained with Encoder-Level KD, especially using contrastive loss, significantly improves over training from scratch. Incorporating audio-only data further boosts performance, achieving results comparable to the teacher model with much fewer parameters. The paper concludes that the proposed KD method for AAC effectively learns an efficient student model from a large-scale teacher model. By focusing on the encoder component, the study addresses the key bottleneck in model compression, ensuring that the student model maintains competitive performance with significantly reduced computational requirements. The framework demonstrates the feasibility of deploying high-performing AAC models on resource-constrained devices, making it a valuable contribution to the field.